Okay, so we have to move on to the organic question very quickly. So, right, so ABC are three isomeric hydrocarbons. So we have A, B, C, C7H14. Okay, so first point C7H14. The formula is like CnH2n, right? So CnH2n means it gives the idea this is an alkene. Okay, because if it is an alkane, it should be C7H16, where CnH2n plus 2. If this is an alkyne, it should be CnH2n minus 2. But here this is CnH2n. So first idea, this is an alkene. Okay, this is an alkene. Then they are telling compound A shows geometrical isomerism while B, C do not. So the other point is this one shows geometrical. And we know there is a double bond in each situation. There should be a double bond. And one of the double bonds where it is A shows geometrical isomerism. The second thing is all three compounds exhibit optical isomerism. So this is a good point to start. So all these three shows optical isomerism. That is nice. Okay. Then on catalytic hydrogenation, all three compounds yield compound D. Oh, that is very important. Why? Because catalytic hydrogenation, which means we add H2. Here, this should give C7H16. This compound is D. And the important point to understand here, all A, B, C gives the same compound, that is D, which should make you to think that the carbon skeleton of A, B, and C all should be same. Because if the carbon skeleton is different, each of these A, B, C would have given different products like D, E, F. But in this case, it is not. All A, B, C have given the same compound D, which should make you to think carbon skeleton same. The carbon skeleton should be same. Okay. Now we will go back to the question again, right? So ABC all shows optical isomerism, which gives the idea like, so there should be a carbon where there should be 4 different groups. So I can write down like this. There should be 4 different groups. So if you think like this should be like CH3 and this should be CH2, CH3, 1, 2, 3, 4 carbons. So remaining 3 carbons. So there should be one A compound which shows geometrical isomerism, and all compounds should have at least one double bond. So I should have like this, something like this as well. Okay. Now I have to connect these two because each compound should have at least one double bond and the carbon skeleton should be same. Okay. So we'll go to compound A. It shows geometrical isomerism. So if it is showing geometrical isomerism, based on this formula, the double bond can be having cis-trans configuration. So it can be CH3 group like this, showing cis and trans configuration, or either it should be 2 hydrogens like this. So here it should be hydrogen, and this should be connected to this one. Let's see. Okay, and here it should be a CH3 group, and this should be connected to another carbon where the skeleton is optically isomer. This should be a star carbon. But the problem with this structure, because we are going to predict compound A because it shows geometrical isomerism. So I think it could be a compound where there is two CH3 groups on the adjacent carbons of the double bond, or either this one, two hydrogen, because this is the only way based on this structure to give the geometric isomerism. Okay. The problem here is, if you think about the carbon number, there is only 7 carbons. So if you think it can be this structure, 1, 2, 3, 4, already 4 carbons gone. So there should be only 3 carbons here, which makes this part 1 carbon here. If this is a hydrogen, there should be another carbon here, and there should be another carbon here. Now it makes 1, 2, 3, 4, 5, 6, 7. Okay, but in that case, you can see there is a CH3 group here and there is a CH3 group here. So there is no 4 different groups, which makes sense that now this carbon is not chiral, which means it is not optically isomerized. It does not show optical isomerism, which means this structure cannot be. Why? Again, because if I put 2 CH3 group, now here we have 4 carbons, so remaining is 3. So I have to take 1 to make it chiral. So other 2 I have to put like this, or either I have to put like this, CH2, CH3. At the same time here I have 2 hydrogen. So still it does not become chiral at this case. Okay. So this structure cannot be. So I am going to cut it. Okay, so the next idea is the double bond with 2 hydrogen and 1 CH3. And here this should be connected to a carbon where there are 4 different groups. So here there is 1, 2, 3 carbons in the double bond chain, 1, 2, 3, and 4 is remaining, 1 is here. There can be 3 more. So I can put 1 hydrogen here, 1 CH3 here, 1 CH2, CH3 here, to make this carbon chiral. 1, 2, 3, 4, 5, 6, 7. 7 carbons. Hydrogens 1, 2, 5, 6, 9, 12, 14. So it's done. Okay. Try to understand the way that I started. I started from where? The compound that is C7H14. All compounds should have 1 double bond at least. All compounds should undergo catalytic hydrogenation to form the same compound D. So it should have the same carbon skeleton. Then I try to start with the geometrical isomerism. So the most possible way to have a geometrical isomerism is either having 2 hydrogen on adjacent carbon of the double bond or 2 CH3 groups. You cannot have 2 CH2 CH3 groups on adjacent carbon, because then already 6 carbons gone, there will be only 1 carbon. It cannot show optical isomerism. So these are the 2 possible things, 2 CH3 or 2 hydrogen. And in fact, if you have 2 CH3 groups, this chiral carbon cannot be taken as chiral centers. So the only possible way is this. This is the only possible way. So this compound should be A, because it shows geometrical isomerism cis, and if you put hydrogen here and CH3, it shows trans, and it shows chiral as well. Okay. Now you should understand B and C should have the same carbon skeleton. This one. Okay. B and C should have the same carbon skeleton because it gives D upon catalytic hydrogenation. But sure, yeah, I can send you the recording because I am recording it. Okay, So this should have the same carbon skeleton because A, B, C all gives the same compound D. Okay. Now there is a fact which says B and C does not show geometrical isomerism. So there is a problem here. It does not show geometrical isomerism, which gives the idea where this double bond should change in the same carbon skeleton. Okay, this double bond should change in the same carbon skeleton where B and C does not show the geometrical isomerism. So can you think a way where the carbon skeleton is same and you can just need to change the double bond so as it does not show geometrical isomerism but it shows optical isomerism. So the easiest way that I can see here, if you change this double bond here to here, okay, that will be 1. B, that is 1. Okay, so it was like this. And in the same way, so first thing is change the double bond to here. So there will be 2 CH2, there will be 2 hydrogen on the same carbon. So it cannot show geometrical isomerism, but still it is chiral. That is 1. The second thing is you can put this double bond here. Because still if you put this double bond here, it will not show geometrical isomerism, but it will show a chiral center. Okay. So the other 2 structures that is possible. So we have this chiral center H and CH3, and this can be written as now CH2, CH2, there will be CH here, and there is the chiral center here. CH2, CH3. This is 1. Because now still we have the chiral center, but no geometrical isomerism. Okay. 1, 2. I'll put like this. 1, 2, 3, 4. And next, the double bond is here. So it will be CH2, hydrogen, yeah, CH2, which is connected to our chiral center, H, CH3, CH2, CH3. So we have the same skeleton, but 3 different compounds. Okay. So we are up to the ABC compounds. Then we can identify D as well. So when you do the catalytic hydrogenation, so it will be CH3, CH2, then CH3, and there is hydrogen like this. I will shift hydrogen here, and there will be CH2, CH2, CH3. So this is our D. Okay, so this can be taken as D, and this can be taken as C. Okay, and then we have all these necessary informations that is given. On treatment with bromine, followed by dehydrobomination with alcoholic KOH, okay, A forms 2 compounds E and F, B forms compound G, and C forms compound H. All 4 compounds have same molecular formula C7H12. That is very simple. And compound E shows geometrical isomerism again, while FGH do not give the structures of EFGH. So we will come slowly, Bryce. Okay. So it says on treatment with bromine followed by dehydrobomination with alcoholic KOH, A forms 2 compounds E and F, B forms G, C form H. So we'll come to that. So very easy it is. Okay. Now because now we have the structures. Okay. Now we have to predict the answers. So D, I will erase D because D is not needed now. So the first reaction is bromination. So I will put bromine here, and there will be hydrogen here and hydrogen here. That is one. And here I will again erase this double bond, and there will be bromine here and bromine here. And here there will be bromine here and bromine here. There is no double bond. So this is the first reaction. And second reaction is dehydrobromination, that is the reaction with alcoholic KOH. Okay, and they say A forms two compounds. Now think about A. Now this is A. Okay, so when you put alcoholic KOH, what can happen here? That is the idea that you need to do. Alcoholic KOH removes HBr. So initially, HBr can be gone from these two and these two, which gives the formula for us triple bonded carbon. Okay, same HBr from these two. Or either it can remove Br from this carbon and hydrogen from this carbon, and one Br from this carbon and one hydrogen from the adjacent carbon. So which makes us the bridge, like this carbon and this carbon will have a double bond, and there is a single carbon, and this carbon and this carbon will have a double bond. Okay, now here this is an alkyne, this is alkene with two double bonds. Okay, so think about that. Alkene with two double bonds means surely now this compound should show the geometrical isomerism, because when you think about this compound, where compound B, it can, here it should go with this one HBr, and it should go with this one. Okay, so in fact there will be a triple bond here, and here also there will be a triple bond in the skeleton. So this compound forms two double bonds. That is one product, and there is another one which forms the triple bond. That is the two products that they are talking about, E and F. Okay, it shows E and F. A forms two compounds E and F. Those are the two products from A. B forms compound G and C forms compound H. So B forms compound this and C forms compound this, where there is a triple bond here and triple bond here. And all have the same molecular formula C7H12. That is correct, because all here there is triple bond, but here there is two double bond which is equal to one triple bond. And lastly, compound E shows geometrical isomerism. So this compound where we have two double bonds, this should be then E and this should be F. That is the way to predict. Okay, so this is a very nice question because it completes all the necessary information that you need to know about the formula first. Second one, about the chain isomerism, because here you saw the chain should be very similar in all cases, and it shows the positional isomerism of the double bond changes, and it gives the idea of optical and geometrical isomerism. So this is a very nice complete question where they have tested all the things on isomerism from a single question. So this question was very difficult for many students because you have to find a point to start. That is the most difficult thing, because you can start with the geometrical isomerism part, you can start with the optical isomerism part, you can try to draw the carbon skeleton first and start. No, don't do that. Try to figure out each point from each statement, then try to finalize your conclusion. Okay, so please go through this video. I will send you the video if you want, and try to figure out the final things. Okay. Right. So next one. So I hope you understood the question well. Okay. So the next one is give one chemical testing test to distinguish between F and G. So F and G, you need to understand here is what is F, what is G here. So this is F and this is G. Okay. This is F and this is G. So F, there is this triple bond and there is a CH3 group here. So easily you can identify this alkyne does not have a terminal hydrogen which is acidic, but this alkyne has a terminal hydrogen which is acidic. So it is very easy to distinguish between this and this by using a normal silver, ammonical silver test or ammonical Q+ chloride test. Okay, which gives the idea F will not give a precipitate either if you use ammonical silver nitrate white precipitate or ammonical Q+ chloride red color precipitate or chocolate brown precipitate. But here you will have a precipitate that is formed. So that is the easiest way to identify the compound. Okay. So yeah, so that's it. So this is a very nice question. Please go through it very carefully because this will give you a lot of information. In fact, total information about the isomerism part, in fact. Okay. So the last one is very straightforward and easy. You have given some reactants and the reagents that you need to predict the type of the reaction and the major product. Okay, so I will go through this very quickly. So the idea is you have benzoic acid with that is a carboxylic acid attached to a benzene. So you add conc nitric and conc sulfuric. So you know the reaction. This should be the nitration. So benzene, the characteristic reaction is electrophilic substitution. Because first an electrophile is formed, then benzene attacks the electrophile. So the electrophile that is formed from conc nitric and conc sulfuric is NO2 plus, and this NO2 plus is attacked by the benzene 5 electrons to replace a hydrogen by NO2 group. So which is the substitution. So this is electrophilic substitution, which is called the SE reaction. But you know, to find the major product, carboxylic is a meta director. So NO2 that should be added to the meta position. Okay. Try to remember that. The second one is HBr addition. So it is an electrophilic addition reaction. Straightforward. So the major product should be according to the Markovnikov rule, where there should be CH3 group at the terminal and there should be bromine atom to the middle carbon. And there is an aldehyde reaction with H plus KCN. So automatically you should remember KCN. There should be a nucleophile form, and this nucleophile can be added to the aldehyde, forming the major product giving CH3, COH, CN, and H. Okay. So this is a nucleophilic addition. Why addition? Because carbonyl carbon is sp2. So you can add CN to the carbonyl carbon, which is sp2, and now then you can add H plus to make it O minus to OH, which forms the sp3 compound, which is the nucleophilic added one, right? So you have CH3, CHO, CN minus can come and attack this. So this will form CH3, CO minus, and H is here, CN is here. So when you add H plus, it will become OH. So this is the product, major product that is formed. And you add alcoholic KH to the brominated compound, and you know HBr should be eliminated. So this is an elimination reaction, and this should happen according to Zaitsev rule, where the adjacent hydrogen is taken out from the carbon where it has the minimum number of hydrogen. Okay, so in this compound, if you take this compound, okay, so if you check this compound, this is the compound that they have given, CH3, CH2, CH, Br, and CH3. Okay, so this Br can be replaced with either this one or this one, but the Zaitsev rule says that you can check the number of hydrogen adjacent. This has 2, this has 3, so it should be this one, the major product, this one and one of this one. And if this goes with this one, then it will form CH double bond CH2. So this is a minor product. The major product is this, because lowest hydrogen is for this carbon, so this hydrogen goes with Br, and highest hydrogen is for this carbon, this hydrogen goes with Br, means it's the minor product. Okay. And the last one is CH3CH2I. So KCN, again, it will form the nucleophile CN minus, and it will attack iodide to replace iodide by cyanide. So it is a nucleophilic attack, and it is not an addition like the third question. It is now a replacement. So it is a substitution reaction. Okay. So try to understand that. So this summarizes and finishes all questions regarding question number 4. So structured essay part is done now. So this structured essay is very long. You can see. In fact, the last question, organic, is very small, but when you analyze the question, you can see there are a lot of points that you need to know. In fact, the part B is very easy because it has given to just to take all the at least 30 marks of the question. Okay. Part A, if you can get through this question, part A, then you are very good at your isomerism part. Okay. So I will quickly come to our organic chemistry question. Okay. Where is it? So because we discussed the organic one, so we will quickly go to the organic chemistry question. Okay. So this organic chemistry question, you can see it is very small. So, and this question is very easy as well. Why this is easy? Because in the structured essay, the part A is little bit hard and you may take some time to do it when you understand the situation. Okay. So again, I will quickly use the board. That will be very easy for me to discuss this. So the question is about the preparation of the Grignard reagent. Before I told you in one of the previous classes about the Grignard reagent, if you have some acidic compounds, the Grignard reagent is destroyed. So that is why in most cases when you have this Grignard reagent, the formation of Grignard, we use like magnesium in dry ether, because in aqueous solution many times you will have some H+ ions from. So first you make the Grignard reagent in ether, then you use the reaction. Okay. So this question tells that the Grignard reagents are prepared by reacting alkyl or aryl halide, yes, in magnesium dry ether. However, the Grignard reagent given below cannot be prepared using the reaction. So why? Explain it why. So the simple of the explanation is you can actually consider about the reaction that can happen when you add these two. Okay. So you have the compound that is given CH2, 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 Br. And here there is OH. So alcoholic OH, it has a certain acidity. So that is why this Grignard reagent cannot be formed, in fact. Okay. So when you add magnesium dry ether, So this will form OH, CH2, 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 MgBr. That is correct. This will form. But the problem is, hence this OH can be present in the solution. What is going to happen here is there will be an OH that is coming here. Okay. And this Grignard is now going to be destroyed by this hydrogen, because this is an acidic hydrogen. This acidic hydrogen can react with Grignard, if you can remember your Grignard chemistry. So what it can form is, yeah, OH, CH2, CH2, CH2. It will form this compound, alcohol. Plus, here it will be CH2, CH2, CH2Br. And here there will be OMgBr. So this hydrogen is given to this compound to form this, and this MgBr is replaced by this. Now here this is not a Grignard reagent, and this is an alcohol that is formed. So when you mix these two compounds with magnesium triether with this alkylated brominated compound with having an alcohol functionality, this is the problem that we have. And remember, this is not the only problem. Any acidic hydrogen will go like this. It will destroy Grignard. Okay. So when you want to use Grignard, first you have to prepare it separately without the compounds having acidic groups. Then you need to add to the reaction medium. That is how it goes. Okay. So why it cannot be prepared? Because you can write down this reaction and state Grignard with this H plus of the alcohol, acidic hydrogen of the alcohol, is destroyed to form this, and the major product is this. Okay. And this will continue like this. Now this Br again react with MgBr and again replaced by another one. So continuously it is broken. Okay. And the second question is, provide a mechanism for chlorination of benzene. So this is very straightforward. So this one you should know very well at this point of the discussion. The only thing is just try to write down several times mechanisms and try to bring all the information together. Okay. So FeCl3, the mechanism for chlorination, you need to first understand chlorine reacts with FeCl3. You have FeCl3, then one of the lone pairs attacks this one, and it will form Cl plus, and FeCl3, there is a minus charge here, and then you have the benzene ring. Okay, right, then you have the benzene ring. So this benzene ring will attack this chlorine, and this will break down like this, and it will form a compound like this. You have hydrogen and you have chlorine, and there is a positive charge here. Okay, then you need to show the resonance structures. There is a positive charge here. Then this one will broke like this. I don't want to show everything, but I will show. Okay. Then finally, from the compound that is formed here is FeCl4 minus, so FeCl3Cl. There is a positive charge here. Now, when you break down this charge, there will be a negative. So this will attack this H plus, and this bond will broke like this, and this is broken like this. So finally, you have three products. One is chlorobenzene, one is HCl, the other one is FeCl3. The important thing about a reaction mechanism, remember, you cannot lose arrows. You need to put all arrows. Second, you cannot lose species. For an example, the reaction of this one should form this. Or either you can just write down chlorine plus and FeCl4 minus. Always, in each step, the number of species in the reactants and the number of species in the products should be same. Okay. For an example, you might write when in this reaction you might write, okay, this reaction happens and finally benzene, chlorobenzene and FeCl3 is formed, and you forgot to write HCl. Okay, you forgot to write HCl means there is a problem. What is the problem? Reactants in the reaction side, number of reactants is not equal to the number of products. So this is wrong. Every time you need to write down all the reactants and the products at the same time. Okay. So part C, using only chemicals given in the list, show how would you carry out the following conversation. So again, we will see the reaction and we will try to go through this very quickly. So we have the, okay, we have two hydrogens and you have given the compound this, and we have to prepare 3CH3 group like this, and you have carbonyl O CH3 thrice. This is the product, right? 3CH3. Then there is a ester. Okay, so okay, now if you can remember in the last organic question discussion, I explained to you, try to come from the front and try to come from the bottom and try to combine if that is the case. Okay, so when you think about this product that is given, okay, when you think about this product that is given, so this is a double bond. So easiest way is to understand this is there can be a cleavage here. When you add, there can be a cleavage. Okay. One can be an alcohol, the other can be a carboxylic group. So I can clearly understand when you do the hydrolysis here for ester hydrolysis. So this part should be CH3 carboxylic group, and this part should be alcohol. Okay. And now clearly I can see a similarity. There is a similarity between these two groups, and one is converted to a carboxylic one and one is added to an alcohol group. So there is a similarity. Okay. And now I have the reactant as only this. Okay. Now think about the reactant and the reagents that is given. Okay. So if I check the reagents that is given, I have sulfuric acid, PCl5, and magnesium ether is also given. So which gives me the idea. So okay, Grignard can be formed. And I have given K2Cr2O7, which can be used as an oxidizing agent. So if I have a primary alcohol here, I can think about an oxidation towards the carboxylic group, right? And also I have given another compound that is the important compound here, that is formaldehyde. So you can now come to a certain conclusion, like, okay, if I have a Grignard, I can attack this formaldehyde to form a primary alcohol. So the first thing is to make a Grignard from this compound, where you need to understand this group should be formed because there is a tertiary carbon. Here Can you see a tertiary carbon? Can you see a tertiary carbon? If you add a hydrogen to this one, according to Markovnikov rule, and OH to this one, I can see a tertiary carbon, which can be very similar to this one. Okay. So to get this compound from this compound is easy. That is, just want to hydrate the compound. So if I add dilute sulfuric acid, it will form CH3, and this carbon contains this CH3, this one and this one, and this double bond is now converted to single bond. Sorry for that. So these two are CH3 groups, and this carbon is this, and here there will be a hydrogen added, so this will be a CH3 group, and there will be this OH that is added. So this compound is here. You can see that this compound is here. But how can I go from this compound to this compound? That is the next idea. Okay. So this is where magnesium dry ether comes. Okay. And you know, magnesium dry ether cannot react directly with this one. So that is why they have given first PCl5. Okay. So this should be CH3, 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 Cl. Now you have magnesium dry ether. This should be MgCl. And now you have the formaldehyde that you can attack here. So you can put the formaldehyde because you have the Grignard reagent. You can put the formaldehyde and it will form the O minus, and you can add now H2SO4, diluted H2SO4 to form the 1, 2. So it will form CH3, 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 CH2, OH. Now you have the primary alcohol which can be oxidized to carboxylic acid. So you need an oxidizing agent. So that is the oxidizing agent that they have given. So you can diluted H2SO4, K2Cr2O7. This is the oxidizing agent that gives this, and finally this. You can add these two. So you can see in this question, all reagents that are given has been used. Okay. So they have given the minimum list of chemicals, and all chemicals can be used here. The only idea here is to identify how to get this tertiary carbon. And this tertiary carbon from here can be easily taken by the hydration of water using H2SO4. Okay. So this is one of the questions. Okay, so that is done. And the next one is also very similar. If you do this one, the next one also very similar question. Okay. So next one we have already given a product. So that is CH3, CH2, CO, NH, and we have CH2, CH2, CH3. And we have the reacting compound, that is propanol. 1, 2, 3. Propanol. So we have propanol, and we have to take this one with this one. So what can be the easiest way to take this one and this one? In the same way as the previous question, I can hydrolyze this. Okay. I can hydrolyze. So if I hydrolyze this, I can write down this as CH3, CH2, CO, Ca plus CH3, CH2, CH2, NH2. Because if these two reacts, there will be an HCl molecule that is going out. Or if this is OH, and if this is the amine, there will be a water molecule that is going out. Okay, so you can think about both. Now, the next idea is how can I come from this to this and this amine? Or either this one and this one. Okay. So how can I prepare this amine from this aldehyde? What do you think about that? Here there is 3 carbon. Here there is 3 carbon with NH2. How can I come to that point? Can you suggest? So the easiest way to do this, if you oxidize this aldehyde, try to understand what I am saying, right? If you try to oxidize this aldehyde, it will be CH3, CH2, COOH. Okay? Which can be this one. Okay? But you need to go towards the amine. So the easiest way to go towards an amine is to make the amide and you reduce with lithium aluminium hydride. That is the easiest way. Okay, so if you have this one, you can just go with this one, COCl, then you add ammonia to form the amide, and you reduce with lithium aluminium hydride, and it will form CH3, CH2, CH2, NH2. Okay. Now, why I am suggesting this path? There can be many different ways to make this one, but why I am suggesting this path? Because when you go through this path, automatically 2 compounds, this one and the final compound that is necessary, is already formed through this mechanism, and here this one is formed here in the first step. For an example, oxidation with H plus K2Cl2O7. Okay, but my suggestion is try to use this one and this one, because the reaction will be more or less complete if you have this COCl instead of COOH. Okay, because removing an HCl is easier than removing a water in this particular type of reaction. Please try to understand that. Okay,